Hello everyone, welcome to day 9 of the 100 day FPGA series. In this video we are going to be looking at adder and subtractor. So these two are one of the most essential combinational logics that we need to basically master in digital electronics, and we will put them on the FPGA and see when they're working. We'll also verify it using a test bench, so test bench verification will also be done. And in subtractor case it will be interesting to see how we are handling the negative numbers and all. So let's get started in the video. So an adder will be something like this. This will be the adder block. There will be inputs and inputs A and B and an output. So A minus B or A plus B will be performed here for the adder. So the width of these two ports can be anything. So on our Xilinx FPGA we have basically a total of 16 switches. Okay, so what I will do, I will assign 8 switches for A and 8 switches for B. So we will create an 8-bit adder for A and B, and the output here, when you are adding two 8-bit numbers, the output will be 9 bits, right? We will have to save one extra bit for the carry. Let's say we are adding 256 and 255 and 255. So the addition result will be represented in cannot be represented in 8 bits, right? Anything like 255 plus 1, even you need to go one extra bit. So whenever you add two n bits number, the sum will be always n plus 1 bits, right? We also have 16 LEDs on the our Xilinx FPGA, so we will be having enough LEDs to basically show the result. So we'll be doing that, and yeah, let's verify it. Let's go into Vivado. So I'll use a Notepad++ to edit my code. Here we will just write our code and paste it in our Vivado. So 8-bit adder, and we'll do let's save it first. Type you have to do Verilog, okay, and then only it will support the formatting. So here we'll do module and module name. So we will have adder underscore 8 underscore bit, whatever the name you want to keep, you can keep here. So the input and output ports we need to define here. So let's define all the ports. I will have A and B. Those are the two numbers that we are going to add, and we are going to have Y as our output, right? And module here, and now here we will define input A. Okay, so I'm going to do the width is 7 down to 0, 8 bits, right? And again input, and I can simply do assign Y equals to A plus B, and Y I need to do output. Here we will have to do 8 down to 0, 9 bits in total. So we will have Y, and this is the final adder code. We'll just write A plus B, and this will implement the 8-bit adder. This is like very nice, right? And this Verilog, this is the strength of Verilog. Like, so again, we do not need to make a truth table about adder and do the expression and all data flow, right? This is again behavioral kind of thing going on here. You can just write A plus B, and the synthesis tool will again interpret it and basically create the circuit for you. Okay, so what we are going to do, we'll take this out of here, and I'm going to first off create a project. I'm going to select Nexus. So here I'll paste my code, and this is the code. Now let's write the test bench for this code. So the next thing is writing the test bench. Okay, so test bench as well, we can just edit in here. So I'll write 8-bit adder test bench. So the first thing that you write in a test bench is basically time scale derivative, right? Directive, time scale directive, right? So you have take time scale, let's stick with 1 nanosecond / 1 picosecond, and this should do it. Here I need to do Verilog and just save. So now you can do module db underscore a test bench has no inputs and outputs. Okay, so the first thing that you do in a test bench is to instantiate the duty, right? So duty instantiation needs to be done. So take the duty name, and here write this. So we have 3 ports, we need to connect them all. So just we are going to define it. So there are 2 methods of writing connecting the signals from here. Till now I have used the dot operator. I'll just use the other method, right, which is following a sequence, right? So if you go into the duty, here you can see A, B and Y is written. So here also if I write it in the same order, it will be directly mapped. Okay, it won't be you don't need to add dot here. We add dot because we have a clarity, because if I don't write dot here, you need to check the duty, right, the sequence. So we generally avoid this kind of declaration, sequence based, but and follow dot one as well. But here since the design is very simple and I wanted to show this as well, so we can stick with this here. Okay, so just take it here, and now I'll change the inputs and check the output. So input, so here again we are going to have lots of combinations of A and B, right? And I can go into adding a for loop and checking all those combinations, but I don't think it's worth it right here. So I'll just what I will do is I'll do 3-4 combinations, different combinations. This won't do a full verification, right? So because because you haven't tested all the possible combination of inputs. Generally for verification you need to verify the design entirely, right? You cannot just check 3 or 4 inputs and check the output, right? So what in that department basically we have randomization and system Verilog and stuff that we use to check the design robustly. Here, since we just want to see whether our design is working, behaving correctly or not, we will just use 3 or 4 inputs, and let's see what we get here. And after changing your inputs, you need to stop the simulation. So $stop over here. So we are done with the test bench, and again I'm emphasizing this again that this is not the complete verification, right? This is just checking whether the DUT is performing the way it is supposed to or not, right? So we'll just take it, and here what you can do, basically you can go into add simulation sources, and you can add files, and the file that you had created you can directly add it from here. So I had saved it onto my documents. I'll choose that file and I'll click add, and it will be directly added, right? So this is how we will be doing it. We'll create the file and we'll add files. Okay, we'll not create a separate source and then copy paste it. We'll just simply add the file itself. And here you can see so here you can see the test bench is added, and I'm going to run the simulation and run behavioral simulation. So here if we expand it, we are seeing the hex values. So here's how you can change the Radix. Okay, so you go in here Radix and just do the whatever the format you have chosen, right? So here I've chosen unsigned decimal, so I'll just take unsigned decimal and Radix, go to unsigned decimal, and I'll go to unsigned decimal here as well. So everything is changed into unsigned decimal. So this is how you change the Radix in Vivado. And here you can see 10 plus 20 is equal to 30. The answer is 30. 11 plus 14 is equal to answer is 25. 5 plus 4 is 9, and 1 plus 12 is 13. So this is how it is performing. It's performing nice, as you can see. Next we will add the constraints, and we'll generate the bitstream of this file. So I'll take the first 8 LEDs as the number 1. First it switches as the number 1, and the next state as the second number, that is B. Okay, so I'll copy all the switches, and here one by one let's change this. If you hold control and drag, you can basically select through the columns, right? So the switches are done. Now we will add the LEDs for the results, and if you go into the LEDs, we need 9 LEDs, so we'll take the first 9. So Y0 to Y8. Okay, so this is the constraints is done. Let's run the synthesis. If you click the generate bitstream, it's going to run all the 3 steps, synthesis, implementation and bitstream at the same time. So directly hit generate bitstream, and the bitstream should be generated. So by the time the bitstream is getting generated, let's talk about the test bench again. Okay, so if you see here, we actually have 8 bits input. The 8 bits, 2 of the 8 bits input. So the number of combinations for this A is basically 2 to the power 8, and you multiply with 2 to the power 8, right? So this is 256 into 256, which is 2 to the power 16, which will be 65,536, I think. So these many number of combinations are there of A and B. So writing these many things is not possible. Even if you generate the waveform using for loops, it will be hard to check it manually, right? You can set up a condition in the after for, if you have 2 for loops, and here you can check the condition that if the DUT, if the output given by the DUT is equal to the A of I plus B of J. If you are entering this into the design and you are getting Y of let's say Y from the DUT, this Y should be equal to the added. So this thing can also be done. In fact, let's do this as well in the test bench. 65,536 combinations are being made. This is not impossible thing for a computer to do, to check all these combinations. So other thing that may happen is when you have lots and lots of inputs, right? Here we only had 2. When you have a lot of inputs, what you end up having is basically a lot of combinations. So checking all those combinations sometimes is not practical at all. Like even the bigger machines are not able to do it. So in those cases, what we do is we do constrained random tests and all in the verification. Okay, so that we will see in later parts when we do very heavy designs. Okay, so in that I will tell you about random tests as well. In fact, in some of the smaller designs as well we can try it. So today let's check, let's perform this manual checking as well and print all the values which are not equal to this. So we'll check this as well. Other than that, the bitstream generation is completed. So let's put this on the FPGA, and after that I will tell you this thing, test bench thing. Okay, so let's put this thing on the FPGA. So here's my FPGA board. I'll turn it on and connect it. Now I will program it. Now the FPGA is programmed, and these 8, the first 8, 1 2 3 4 5 6 7 8, so from here to here this is one number, and from here to here this is another number. So right now 0 from 0 0 0 0 0 and all zeros are getting added, so you are getting 0. Let's say 0 1 is added to 0 0, we are getting 0 1. What if 1 is added to 1, say, right? So if we have, like, I'm putting my fingers so as to remember which where's the division between the two numbers. So here I think this one is 1. Yeah, so here as you can see 1 is added with 1 and we are getting 2. So what if 1 is added with 3? So we should get 4, right? If we add 1 with let's say 5, we should get 6110. So as you can see here, we are getting all these. So whatever you want to add in binary, here you can just add it and you can check it here. So for last thing, what we can check is, we can check the overflow, like 9th bit is when it is on. So if we have 255 added with 1, we will get 256 and the 9th LED is on. So this is the one extra LED that we have to assign, right? So this is the FPGA implementation of 8-bit adder, and we will do subtractor now. So for doing the subtraction, what you can do is basically replace the plus with minus, right? I'll do A minus B. When you basically have A and B, to do proper 2's complement subtraction and all, we have to do signed. Okay, so both the inputs and outputs are signed. You have to add the signed, because right now what it was doing is it was subtracting two unsigned numbers, right? So here we can't enter minus 10 as the input again, because we haven't declared it as signed, right? So when we declare it as signed, then we will be able to do all those things. So if you go into adder, here you can do minus 10, minus 20, 14 minus 14, like 11 minus 14, these kind of things we can do. And if we relaunch the simulation, here you can see minus 10 minus 20 is minus 30, right? So here's the thing, look at this. When we remove the signed keyword from here in the minus, when we are doing A minus B, and when we are giving the minus 10 as input in A, here you can see the minus 10 minus 20 is not minus 30 this time, because the number minus 10, even though we are saying minus 10 over here, we are saying minus 10 because we have set the radix to signed, right? What is actually happening is it is taking it as unsigned. As you can see here, 246 minus 20 is 226, right? So it is taking it as fundamentally unsigned, right? It's the behavior of the DUT. So you have to add signed, otherwise you cannot input minus. Okay, so earlier when we had entered the signed keyword, we were able to write minus 10 minus 20 and the answer was minus 30, right? So this is the difference. So whenever you do subtraction, you have to keep this thing in mind. And whenever you add, even when you add, when your inputs are signed and your outputs are signed, you have to be careful. When you overflow, you will basically flip the sign. That's the thing, right? So this is very tricky thing to handle, signed and unsigned numbers in Verilog, and we often face this issue, this signed and unsigned issue. We see signed overflows all the time when we do FPGA projects, right? So this is one of the main things that you need to keep in mind. Like everyone faces this thing when they are doing FPGA projects. So I'm just telling you from the forward only that please keep this thing in mind. Whenever you have signed number, you make it signed keyword, you add the signed keyword, and in the output you make sure that it is not overflowing, right? That addition of two numbers, if they are getting overflowed, then you are like, the output will be turned into negative and the entire behavior will change. So this is one important thing that I wanted to share. And the last thing that I will do in this video is basically show you how to do exhaustive verification. So exhaustive verification in the Testbench you can do. What you need to do is, so here you just do for loops. Okay, so I'll do integer. So we have 8 bits, right? So we can go up to 0, from 0 to 255. So here what I'm going to do is I'm going to give the input to the DUT. So the DUT's input is A and B. So what I'm going to do, A equals to I and B equals to J. Okay, so it will take all the combinations of the inputs possible, and what we are going to do is we are going to check here only if Y, which is the output from the DUT, if Y is equal to A plus B. Okay, this is different. See, we are adding A and B here. Okay, I can do I plus J here as well, but since I and J are equal to A and B, we are just doing A and B. So A plus B. Here I am checking if the output from the DUT is equal to the two numbers that we have entered into the DUT, addition of the two numbers, right? So this A plus B is happening here locally, and the Y is coming from the DUT. So this is what we need to check, and here you can simply write if these two are equal, then I'm going to display. So for displaying, you are going to do $display. Okay, so simulation is done, and so the messages that you have printed will be available on the tickle console. So if you see, not correct. Okay, yeah. So here you can see that A and B are changing, but we are basically checking at the time of assigning itself. So there will be some propagation delay which we need to account for. So what I'm going to do is, just after I set A and B, we are going to have a delay, a very small delay, and here the total delay I'm going to give is 10. So I'll just do 9 over here, and when I relaunch the simulation now you can see all of the values are correct, right? So what's happening was we were setting A equal to I and B equal to J, and immediately checking Y is equal to A plus J. So Y will change after some time, so that delay is compensated when we add a 1 nanosecond delay. Shown you how you can exhaustively check the 8-bit adder, and I've also shown you how the subtractor is working and the common thing that you might miss when designing a subtractor, right? The signed and unsigned stuff. And I encourage you that you basically do the same, do the subtractor and put it on the FPGA and check, and especially check the carry bit, okay? If the carry bit is performing right or not. So this is it. This is for day 9, where we have implemented 8-bit adder and subtractor, and we have checked through the test bench whether it is behaving correctly or not, and we have done a full exhaustive verification as well, right? And we have implemented the adder on the FPGA. So thanks for watching. We'll see you on day 10 regarding a binary to gray conversion, and that conversion thing will be very nice. After that, we will focus more on some of the more combinational logic as well, and we'll finish combinational logic and we will enter sequential logic. So that is our goal. So see you tomorrow. Thanks for watching.